Day 2b. Solid state. Solids have definite volume and definite shapes. Particles are held together by fairly strong force. Therefore, they are present at fixed position. Solids are classified as crystalline amorphous. Crystalline solids, they have long range order. Amorphous have short range order. Crystalline solids have sharp melting point. Amorphous solids do not have sharp melting points. In crystalline solid, they are given cleavage, that is, they break into two pieces with plane surface. Amorphous solid, they are given irregular cleavage, that is, they break into two pieces with irregular surface. Crystalline solids, they are anisotropic because this substance show different property in different direction. In amorphous solids, they are isotropic because of this substance show same property in all direction. Type of crystalline solids. Molecular solids. Lattice points are occupied by neutral molecule. Forces that hold them together are weak van der Waals force or dipole-dipole interactions. For example, solid carbon dioxide, carbon tetrachloride, and most of organic compound. Covalent solids. Lattice points are occupied by atoms linked to each other by covalent bonds. They are strong and hard with high melting points, for example, diamond and silicon, etc. Ionic solids. Lattice points are occupied by oppositely charged ions. Strong electrostatic force of attractions are present. They are hard and have high melting points, for example, NaCl, sodium chloride. Metallic solid. Lattice points are occupied by metal atoms. Metallic bonding is present where loosely bound electrons of metals are attracted by kernels, for example, copper, iron, etc. Crystals. Crystals is a homogeneous portion of a crystalline substance. It is composed of a regular pattern of a crystal of a structure units, ion, atoms or molecule by plane surface making definite angles with each other, giving a regular geometric form. A regular array of points showing atoms or ions in three-dimensional is commonly called as space lattice or lattice. Unit cell, a three-dimensional group of lattice points that when repeated in space generate the crystal is called unit cell. Type of unit cell, primitive or simple cubic SC. Atoms are arranged only at the corner of the unit cell. BCC, body center cubic BCC atoms are arranged at corner and at the center of the unit cell. Face center cubic FCC atoms are arranged at the corner and at the center of each faces of the unit cell. Crystal system cubic, orthorhombic, tetragonal, monoclinic, triclinic, hexagonal, rhombohedral. Edge A equal to B equal to C. Angles alpha equal to beta equal to gamma equal to 90 degree. Example NaCl. Orthorhombic A is unequal to B is unequal to C. Alpha is equal to beta is equal to gamma is equal to 90 degree. Rhombic sulfur. Tetragonal A equal to B unequal to C. Alpha equal to beta equal to gamma equal to 90 degree. SnO2. Monoclinic A unequal to B unequal to C. Alpha equal to beta equal to 90 degree. Gamma unequal to 90 degree. Borax. Triclinic A unequal to B unequal to C. Alpha unequal to beta unequal to gamma unequal to 90 degree. Potassium dichromate. Hexagonal A equal to B unequal to C. Alpha equal to beta equal to 90 degree. Gamma is equal to 120 degree. Lead iodide. Example, rhombohedral A equal to B equal to C. Alpha equal to beta equal to gamma unequal to 90 degree. NaNO3. Sodium trinitrate. Bravais lattice. Bravais stated that there are 14 fundamental and unique ways in which particles can be arranged in three-dimensional point lattice. These are known as Bravais lattice after his name. Crystal system: cubic, Bravais, simple, body-centered, face-centered; orthorhombic, simple, body-centered, end-centered, face-centered; tetragonal, simple, body-centered; monoclinic, simple and face-centered; triclinic, hexagonal, rhombohedral. Contribution of different type of particle to the unit cell. Location of the particle. Contribution to the unit cell: body center 1, face center 1/2, air center contribution is 1/4, corner is contribution is 1/8. Total number of particles in different unit cell. Unit cell contribution number of particle. Simple cubic contributed 1/8 multiplied by 8 equal to 1. At each corner number of particle is 1. BCC contributed is 1/8 multiplied by 8 equal to 1. Corner 1 multiplied by 1 is equal to 1. Body center number of particle is 2. FCC is 1/8 multiplied by 8 is equal to gives 1 particle. Then 1/2 particle, okay, in 6 faces is 1/2 multiplied by 6 equal to 3. Face 3, face center 3 atom is there, so number of particle is 4. Density of the crystals. Density of the crystals is present by density of the unit cell. Let A be the edge length of the unit cell and N be the total number of particles in the unit cell. M be the atomic or molar mass of substance constituting the crystals, and N be the Avogadro number. Density rho is equal to Nm upon Na cube. Relation between edge length A and radius of the particle in a unit cell are: unit cell relation, distance between nearest neighbor. Simple cubic relation is I equal to A upon 2. Distance between nearest neighbor is D equal to A. FCC is relation is R equal to A upon 2 root 2. Distance between nearest neighbor is equal to A upon square root 2. BCC is relation is equal to R equal to square root 3/4. A distance between nearest neighbor is D equal to 3 divided by 2 multiplied by A. Packing fraction. The fraction of total volume of the crystals occupied by the particle. Packing fraction of the unit cell represent packing fraction of the crystals. Type of unit cell. Packing fraction in terms of pi. Packing fractions: occupy space percentage, empty space. Simple cubics have packing fraction in terms of pi is pi/6. Packing fraction of simple cubic is 0.52. Occupied space by simple cubic is 52. Empty space is 48. In BCC cell, packing fraction is square root 3 pi upon 8. Packing fraction of BCC is 0.68. Occupied space is 68. Empty space is 32. FCC packing fraction in terms of pi is square root 2 pi/6. Packing fraction 0.74. Occupied space 74. Empty space 26. Bragg's law. Study of internal structures of crystals can be done with the help of X-rays. The distance of the constituent particles can be determined from diffraction value by Bragg's equation n lambda equal to 2d sine theta, where lambda is the wavelength of X-rays, n is the order of reflection, theta is the angle of reflection, d is the distance between the two parallel surfaces. Close packing of identical spherical particles. HCP, hexagonal close packing. The spheres are arranged on a flat plane so that each sphere is in contact with 6 spheres at the corner of a regular hexagon called layer A. A second layer B is placed on the layer A such that the sphere of the second layer occupy alternate hole in layer A. The layer A and B are then repeated on as discussed above. This arrangement is called AB, 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 AB. For example, cadmium, molybdenum, zinc, vanadium, etc. CCP, cubic close packing. The spheres are arranged on a flat plane so that each sphere is in contact with six spheres at the corner of a regular hexagon called layer. A second layer B is placed on the layer A such that the sphere of the second layer occupy alternate holes in layer A. A third layer C is placed on the layer B such that the sphere of the third layer occupy the other vacant alternate holes in layer A. The layers A, B and C are then repeated as discussed above. This arrangement is called ABC, 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 ABC. For example, silver, gold, copper, platinum in the above two arrangement. Each sphere has 12 spheres as its nearest neighbor and nearly 74% space is occupied. Type of void: tetrahedral void. It is formed when a sphere fits into depression formed by three other spheres. Closest packed in two dimensions. The number of tetrahedral holes is twice the number of atoms present. Octahedral void. It is formed when three closest packed spheres of one layer is put over three closest packed spheres of the second layer, their position being inverted with respect to each other. The name of octahedral holes is equal to number of atoms present. Radius ratio. The radius of the ratio of the radius of cation to the radius of the anion is called radius ratio. R plus upon R minus. R plus R minus. Arrangement coordination number. Example: radius ratio 0.155 to 0.225. Arrangement is triangular planar. Coordination number is 3. Example is B2O3. Radius ratio 0.225 to 2.414. Arrangement is tetrahedral. Coordination number is 4. Example is zinc sulfide, mercury sulfide. 0.44 to 0.732. Arrangement is octahedral. Coordination number is 6. Example is sodium chloride and calcium oxide. Radius ratio 0.732 to 1.00. Arrangement is cubic. Coordination number is 8. Example is cesium chloride, ammonium bromide. Description of some important crystal structures. Rock salt structure NaCl, FCC arrangement in which chloride ions occupy the corners and face center of a cube, while sodium ions are present at the body and edge of center. Example: halide of lithium, sodium, potassium, rubidium, silver fluoride, silver bromide, ammonium chloride, ammonium bromide, ammonium iodide, etc. Coordination number: sodium plus cation is equal to 6, fluoride minus anion is equal to 6. Zinc blend structure: zinc sulfide, CCP, cubic close pack arrangement in which S2 minus anion ions form FCC and each zinc 2 plus cation ion occupy half of the tetrahedral void. Example is copper chloride, copper bromide, copper iodide, silver iodide. Coordination number is zinc 2 plus cation is equal to 4, S2 minus sulfur 2 minus anion is equal to 4. Fluoride structure CaF2. Ca2 plus ion form FCC with F minus anion occupy all tetrahedral void. Example is barium trifluoride, barium trichloride, strontium trifluoride, strontium dichloride, cadmium difluoride, lead difluoride. Coordination number of C calcium 2 plus anion is equal to 8. F minus anion is equal to 4. Antifluoride structure disodium oxide. Oxide ion form the cubic close packing arrangement with sodium ion occupying all tetrahedral void disodium oxide. Exam coordination number is Na plus cation is equal to 4, O2 minus anion is equal to 8. Cesium chloride structure CaCl. BCC arrangement VCS plus at the body center and Cl minus ions at the corner of a cube or vice versa. CsCl, CsBr, CsI, CsCn, Cs plus anion cation is equal to A, Cl minus anion is equal to A. Defect in solid. Any deviation from the perfectly ordered arrangement constitute a defect or imperfection. Electronic imperfection. In the crystal of pure silicon or germanium, some electrons are released thermally from the covalent bonds at temperature above 0 Kelvin. These electrons are free to move in crystals and are responsible for electrical conductivity. This type of conduction is known as intrinsic conduction. Impurity defects. If a group fifth element such as arsenic is doped with a crystal of germanium, 4 covalent bonds are formed using 4 valence electrons, but fifth electron remain free. This electron can serve to conduct electricity when an electric field is applied. It is called extrinsic conduction. Such are called N-type semiconductor. If a group 3 element such as indium is doped with a crystal of germanium, 3 covalent bonds are formed using 3 valence electrons, but the covalent tetrahedral structure is not completed. Some of the sites normally occupied by the electron are left vacant and they are called holes. When an electric field applied, adjacent electron migrate into these holes and this way it conduct electricity. It is called extrinsic conduction, such as p-type semiconductor. Atomic imperfection or point defects. When deviation exists from the regular periodic arrangement around an atom or a group of atoms in crystalline substance, the defects are called point defect. A point defect in a crystals may be classified into following types. Stoichiometric defect. The defect do not disturb the stoichiometry. The ratio of number of positive to that of negative ions are called stoichiometric defect. These are of following types. Schottky defect. This type defect occur when equal number of cation and ion are missing from their lattice sites so that the electrical neutrality is maintained. For example, sodium chloride, potassium chloride, cesium chloride, potassium bromide, etc. Frankel defect. This type of defect arises when an ion is missing from its lattice site and occupies an interstitial position. The crystal as a whole remains electrical neutral because the number of anion and cation remain the same. Since cations are usually smaller than anion, they occupy interstitial sites. Example, zinc sulfide, silver chloride, silver iodide, etc. and silver bromide. Both Schottky and Frankel defect occur. Non-stoichiometric defect. Defect that disturb the non-stoichiometry of the compound are called non-stoichiometric defect. Metal excess defect due to anion vacancies. A compound may have excess metal anion if a negative ion is absent from its lattice sites, leaving a hole which is occupied by electron to the maintain electrical neutrality. The hole occupied by electron are called F center. Metal excess defect due to interstitial cation. If an extra positive ion is present in an interstitial site, then electrical neutrality is maintained by the presence of an electron in the interstitial site. Zinc oxide is yellow when hot, white when cold due to this defect. Metal deficiency defect by cation vacancy. In this, a cation is missing from its lattice. To maintain electrical neutrality, one of the nearest metal ion require two positive charge. Example, transition metal compounds such as nickel oxide, iron sulfide, etc. Metal deficiency defect by having extra anion occupying interstitial sites. An extra anion is present in the interstitial position. The extra negative charge is balanced by one extra positive charge on the adjacent metal ion. Elec- Electrical property of solids. Pyroelectricity, certain crystals at very high temperature show electrical property, for example, tartaric acid. Piezoelectricity, certain crystals develop electricity when mechanical stress is applied, for example, sodium potassium tartarate. Inverse piezoelectric city, certain crystals develop mechanical stress when electricity is applied to them. Ferroelectricity, even at room temperature, all the electric dipoles are oriented in a particular direction. For example, barium titanate. Antiferroelectricity, all the electric dipoles are equally oriented in two opposite directions so that the net dipole moment is zero. For example, lead zirconate. Superconductivity, when current passes through a substance without any resistance. The phenomena is called superconductivity and the substance is said to be a superconductor. Generally, a very low temperature is required to demonstrate superconductivity. Superconductors are diamagnetic. Magnetic properties of solids. Paramagnetic substances that are weakly attracted by the magnetic field. One or more unpaired electrons are present. For example, oxygen, nitric oxide, etc. Diamagnetic substances that are weakly repelled by magnetic field. All electric electrons are paired. For example, vanadium, pentoxide, benzene, etc. Ferromagnetic substances that are strongly attracted by the magnetic field, for example, iron, cobalt, nickel, etc. Ferrimagnetic magnetic dipoles are aligned unequally in opposite directions so that there is a net magnetic moment, for example, magnetic oxide of iron. Antiferromagnetic magnetic dipoles are aligned equally in opposite directions so that there is as no net magnetic moment, for example, ferrioxide, manganese dioxide, etc.